So, as we go to higher energies or higher temperatures, we tend to experience the unification of different forces. The first, so Sean mentioned earlier that there are four known fundamental forces of nature: the electromagnetic, the strong, the weak, and gravity. So the first of these two, the electromagnetic and the weak force, have already been unified in theory and in experiment. And it's been verified that if you go to high enough energies, at some point they become the same force, and now it's sometimes called the electroweak force. So what happens if you go to even higher energies? Then we're down to three forces. Well, the next one is the strong force that is conjectured to become the same as the electromagnetic and weak force. And so when all three of those come together at an energy called the grand unification scale, you get GUT forces. GUT stands for Grand Unified Theory, because it incorporates all of the three, those three, all except for gravity, forces together in the same package. So now we're going to talk about gravity in a minute, but that's further off. So at this grand unified energy, what happens is, let me show you this diagram here. The strengths of the different forces, they vary as some forces get stronger and other forces get weaker as you get up to these higher temperatures. And so, looking at this graph, the three forces, we have all three except for gravity on here. Some get stronger, some get weaker, and then they almost intersect, but then they kind of mismatch. Now there's another thing that happens at higher energies is there tends to be a higher degree of symmetry between things. Instead of everything looking kind of random and haphazard, it gets a lot more ordered, and there's these extra symmetries. So one of the big theoretical symmetries that's been proposed is called supersymmetry, that might be up there at higher energies. We don't have any experimental evidence for this, but it's a pretty popular model, and lots of physicists work on it. So supersymmetry is nicknamed SUSY because it's usually written SUSY, and so that's how physicists usually talk about it. SUSY does this or SUSY does that. It's just so without SUSY, we get this mismatch here, but amazingly, the different strengths of the forces, it seems, intersect all at the same point if you put in supersymmetry. So that's one of the motivations for it, and the others are more technical, so I won't get into them. So if all three of these become the same grand unified force at that energy, then what happens to gravity? Does that at some point become the same as all the other forces? Well, gravity is really the hardest because it's different from the other forces in that it's the curvature of space-time itself, as Sean explained. And presumably this happens in quantized excitations, and there's a particle associated with it called a graviton, but it's never actually been seen, so people are still working on that. And so the energy scale that you would expect, the name for the energy scale that you'd expect gravity to unify with the other forces is the Planck energy scale, or the Planck length. In terms of distances, it's an extremely small distance, probably the smallest distance that you can ever get to. And the reason for that is because in order to probe smaller and smaller distance scales, you have to pump more and more energy into an experiment. So we build these giant accelerators to look at really tiny, fine structure of things. So you have to get higher and higher energies, but at some point you get so much energy that you're putting into this really tiny space that it creates a black hole. And a black hole is kind of the ultimate censorship, where you can't see what's going on. And so we never know what's going on the other side of a black hole. So you can't really put in more than that energy, and you can't really see what's going on in the really hyper-fine structure of space-time below the Planck energy scale. And so that's where all the forces are expected to be united, and we would get what's called quantum gravity. And the most popular model for quantum gravity is superstring theory, which Sean's about to talk about. There are a few alternatives, but we're only going to talk about that one today.
Yeah, okay. So basically it's had the most money poured into it, and so it's had the most research and made the most progress. But it is a pretty interesting theory, and it's really nice and pretty if it does actually work. The idea is that if you look further down, beside, below the size of the atom, below the quarks and everything, that everything up is made of vibrating strings.